Good morning, everyone. Good day, good evening, wherever you are. So the title of today's presentation is BERT's Achilles Heel, Applying Contrastive Learning to Fight Anisotropy in Language Models. Before we start, I want to give a little bit of a background because I'm sure we have people from different cultures. So Achilles is a person from ancient Greek mythology. He was a fighter, a very successful one. He survived many very difficult battles and was perceived as someone super powerful and invulnerable. His story starts with his mother. Story of his invulnerability starts with his mother, Thetis, who dipped him in the Styx River in order to make him invulnerable. So this thing happened, but when she was dipping him in the Styx River, she was still holding his heel, and that was the only part of his body that was not dipped in the river, and that was a part of his body that was then injured and caused his death. BERT is a transformer-based large language model, and it's also known to be very powerful. It's pre-trained on web-scale data in self-supervised fashion, so on like large-scale data. And it has many strong sides, many advantages. It offers many advantages. But the question for today is, does it have its Achilles heel as well? My name is Aleksander Molak. I'm an educator and speaker at Lespire.io. I'm a machine learning engineer and researcher at IronScales. I love traveling with my wife.
Aleksander, are you sharing slides currently?
I thought I am.
So we are currently you're currently not sharing slides, but if you do share, we'll put them up for you.
Let me reshare them. Thank you so much for.
Just
yeah,
coming
that's
up right
that's
now.
an important one. Does it work now?
It does work right now. Yeah.
Okay.
Thank you.
Great. So I will move back quickly. So we talked about Achilles. We talked about his story and story of his mother dipping him in the Styx River in order to make him invulnerable, and his heel, that she was holding him by his heel. That was the only part of his body that remained vulnerable and then became a cause of his death. And then we talked about BERT, a large transformer-based language model that is pre-trained on a huge corpus of web-scale data in self-supervised fashion. And this model has been shown to be very powerful, much more powerful than anything that we knew before, including embedding models and so on. And today we want to ask this question regarding BERT's Achilles heel. Does it have one? And is anisotropy, this secret term, is it a good candidate for Achilles heel for BERT? And if so, can we do something to make BERT less vulnerable? Yeah, so my name is Aleksander Molak. I'm an educator and speaker at Lespire, machine learning engineer and researcher at IronScales. I love traveling with my wife, running. I enjoy good vegan food. And I'm currently working on a book on causality in Python. So if that's something that's interesting to you, you can scan this QR code and learn more. Let's start with a quick agenda. So we'll start with a quick refresher on transformer model. I'm sure that many of you know this model, how it works. But we'll do it anyway for those who might need a refresher. Then we'll talk about anisotropy, what it is, and why it might be something bad in the context of large language models. Then we'll talk about contrastive learning. So we'll define contrastive learning, and we'll also get some context why contrastive learning might be relevant when we're talking about transformer models and anisotropy. And finally, we'll talk about some practical stuff. So how to leverage contrastive learning in order to fight anisotropy, and how to build embeddings using contrastive learning in Python using a library called SimCSE. And finally, we hopefully will have some time for your questions. Okay, so transformer model, what is it? It's in its essence, it's a neural network. It's a pretty complex neural network that has certain properties. So we'll talk about two aspects of transformers today that will be relevant for us. So first, the transformer model is pre-trained on a self-supervised task, which means that we do not provide this model with any labels. We only provide the model with the training data unlabeled, and then we create an objective without adding labels. So we'll talk about this in more detail in a second, how precisely it works. And second, it uses self-attention mechanism. Okay. So this is an example task that can be used to train transformer models. And this is called masked language model. So what we do here, we just collect natural language sentences from whatever the source is. It can be Wikipedia, it can be the whole internet, I don't know, Reddit, and so on. We pass them to the model, and from time to time, we just mask one single word, and we ask model to predict this word based on the context it has. So for instance, here you have two sentences with two different masks. The first one is, this is a mask, and the second variation of the same sentence, also mask is a T. So the original sentence is, this is a T. And we mask those random words from time to time in different ordering. And the second sentence is, John likes to surf. And then in the first iteration, we mask the word surf. And in the second iteration, we mask the word likes. So that's the task. And we'll talk about certain properties of the embeddings that we can achieve using this task in a second. But now let's talk about the second aspect, self-attention. So self-attention allows us to do something very important. It allows us to measure relative importance of words. And the model measures this relative importance automatically, which means this is a part of the training objective. Or to be precise, this is a part of the it measures it through the values of the parameters of the model. So we learn this relative importance during the training jointly with all the other parameters of the model. And second thing is that self-attention allows us to model contextual meaning. What does it mean? In linguistics, we sometimes talk about a thing called polysemy, which means that we can have the same term that has two different meanings. Okay, so one example that I could give you is, you can say, hey, yesterday I went to the bank to pick up my new credit card. Okay, and another sentence you can say is, I spent a lovely evening on the riverbank. Okay, so we have word bank in both those sentences, but the meaning of those words is completely different. In the first sentence, we talk about bank as a building or an institution, and in the second, as a riverbank. Now, why this is important? This is this example gives you like a very pronounced difference between those two meanings. But sometimes the differences in the meaning for the same word might be much more subtle, but still they might influence the way we predict an answer, whatever the answer is. So those models are, thanks to self-attention mechanism, those models are able to model this. So here you have a visualization of self-attention weights in one of the early layers of the BERT model. So what are attention weights? This is a type of coefficient that says how relevant another word is to the current word that we are looking at. So you can see that maybe if we say there, then we have the strongest attention weight to cat. So it looks one step ahead, and it says like, the what? What is the object? It's the cat. And then from cat, it has one attention weight to the CLS token. It's a technical thing. But also another attention weight pretty strong is to set. So cat set. So cat, what was cat doing? It's set, right? So this is how it works, and we can also see that this changes through the layers. So we can see in this animation that attention weights are different in each layer. So in each layer, model learns something new about the connection between different words and how they build meaning. And one very important thing about the representations that we can obtain using models like transformers, but also earlier models like word2vec, is that we map words to a continuous space. So words are discrete, right? Cat is just one word. There's no continuous way between cat and dog in the language. You can say half cat, half dog, of course, something like this. But language is discrete in its nature. So what we're doing with models like transformers, we're mapping words to a continuous space, and we can perform certain operations in this space. And there are a couple key properties of this space. So first of all, words that have similar meaning tend to group together. Okay, so words that have similar meanings should be mapped to points that are close to each other in the embedding space. So we have train, bus, and taxi. We can see that they're very close, but cat and dog are much further from bus and taxi. And yoga and Pilates are kind of far away from king, but close to each other, and so on and so on. And so this is the ideal scenario, and many researchers showed that models like word2vec and all the later models, they have this property. But then all the researchers demonstrated that this property is not always there, or not always to the extent that we wish to. So now let's talk about anisotropy. Okay, this word might sound scary to you, and I think that's natural. It also sounded scary to me when I read it for the first time. So let's take a smaller part of this word, and let's talk about isotropy. So isotropy is a word that is derived from ancient Greek, from two Greek words, isos and protos. And isos means equal, and protos means way, direction. So isotropy means equal in each direction, in a sense. Being a little bit more formal, we could say that it's uniform in every direction. And mapping this intuition to something statistical, we can talk about isotropic Gaussian distribution. So isotropic distribution is a distribution where we go in every direction, in a sense, the same way. So here we will limit ourselves. We'll limit the definition of isotropy to a spherical Gaussian, although this is not entirely true. So we can see that here we have two variables, x and y, and the spread for x and y is like the same in every direction, in a sense. Okay, if we map it to 3 dimensions, we have a sphere. Okay, so the circle gets into the shape of a 3-dimensional sphere. So we have now 3 variables, and they have the same properties. And technically speaking, an isotropic distribution, isotropic Gaussian, is a distribution that has covariance matrix in a form of variance time identity matrix, but this is not very important to us. But non-isotropic distribution will have spread that is not equal in every side. And I'm talking about equal spread, although technically it's not necessarily correct, because the methods that we will discuss in a second will try to build distributions that are isotropic, but are also limited to a unit sphere. Okay, so that's why we're focusing on spherical distributions, multivariate spherical distributions. So we know that isotropic distribution can look like this, for instance, and anisotropic might look like this. And now let's see what happens in reality. So this is a distribution of embeddings for a model called Roberta, another transformer-based model. And as you can see, these embeddings, they form a type of a cone that has like a narrow tip when where we have a large concentration of many different embeddings. So each embedding here might be, each point might represent either a word or a document, right? And when we do certain transformations to these embeddings, we can get much closer to something more spherical and something more isotropic. So this comes from a paper by Luo from 2021, and here they used whitening. This is one of the, like, let's say, transformations. But now let's think about it. What is the cost of getting this this tip so dense here? So this narrow cone might cause that the similar object might get a little bit too close to each other. So for instance, when you talked about train and a cat, in this cone, train and a cat might be pretty close to each other. Maybe not as close as cat and dog, but pretty close. Now, one challenge with this is that if we have this, it might be very difficult to build a decision boundary. So a model will need to build a decision boundary that is very curvy and goes between all those cats and dogs to separate them from trains and buses, right? Because there's very little space. And when the representation is isotropic, then our decision boundary essentially becomes linear, okay? Which means that it will become a hyperplane in high dimensional space. Okay, so let's talk about contrastive learning now. So what is contrastive learning? Contrastive learning is a type of training for neural networks or machine learning models in broader sense, where we use similar examples and dissimilar examples in order to make representations of similar objects closer to each other and make representations for this similar object further away from each other. So here we can see we have like a cat and a cat. So that could be a so-called positive pair for contrastive learning. So we say positive pair means that these objects are similar. We pass them to the network, and the network learns that their representations should be close to each other. And then we have a cat, or like this kitten and a puppy, and we say that they are not similar to each other. We say this is a negative pair, so-called a negative pair. So how do we do it if we don't know what is in the pictures or in the sentences, right? I'm using pictures here because I think they are more intuitive, but the same we can do for words and for sentences. So that's a very good question because maybe we need a model to label those pictures. But the answer is much simpler. So we can actually take one picture and perform two different augmentations of this picture, and use those augmentations as positive pairs, and then take a picture and another picture and use them as negative pairs. Of course, this might inspire you to ask another question. Hey, but what if we take another picture and it's a cat as well, right? And it's a very good question. Well, this will introduce some noise to the model. Now, it seems in practice that this noise is actually not making the model to fail, and maybe it also is also advantageous in the sense that it brings a little bit of regularization to the model. So this looks like this, and this is a another architecture called SimClear for images. You can see that you encode those two pictures using two different networks, and then you maximize agreement for similar pairs and push the negative pairs further away from each other. So, but we are talking about language, so that will be slightly different, but only slightly. We'll talk about this paper. You can scan this QR code if you're interested in learning more. It's called SimCSE, Simple Contrastive Learning of Sentence Embeddings. So how can we do it for language? There are two ways proposed in this paper. The first one is unsupervised. The second one is supervised. And we will focus on the unsupervised one today, but supervised is very, very similar in its essence. And for unsupervised, we essentially use the same sentence. And then for natural language, it's much more difficult to augment the data in a meaningful way, right? We can change some words, we can do all those flips, we can put random words. That's what people are trying to do sometimes, but it doesn't always work very well, and sometimes it can distort the meaning very seriously, especially when we have short sentences. So what the authors have done here is very interesting, because they leveraged the dropout mask in transformer architecture to do augmentation for them. So they embed the same sentence twice without freezing the seed for dropout masks. So dropout masks are slightly different for both embeddings. And then we have slightly different representations, and they are treated as a similar or positive pair. And then we take one sentence and another sentence as a negative pair. And this tends to work pretty well. For supervised learning, what people do is they usually use data sets like SNLI and so on. Okay, so how anisotropy and contrastive learning are connected? It turns out that we can find two different ways of expressing features related to anisotropy, and they are alignment and uniformity. So uniformity means that representations of our images or words or sentences, as in our case, are distributed on the hypersphere uniformly. Okay, and this allows us to preserve maximal information, and this also allows us to build decision boundaries that are very simple. So we can basically use hyperplanes in the idealized case. And the second one is alignment, or the first one is alignment, which means that similar objects are mapped to points that are close to each other in the space. So when we optimize for those two properties, it turns out that we are actually moving towards an isotropic representation. And so as authors has shown, by using contrastive learning objective, we can do this mapping from this narrow cone to this more spherical shape here. And thanks to this, we are also getting good alignment and good uniformity. And how does it work? Here are a couple of different models. So there is SBERT, which stands for sentence BERT with whitening. We have different other transformations like BERT flow, SBERT flow, and so on. And here we have SimCSE. And on x-axis and y-axis, we have loss, the alignment loss term, and here we have uniformity loss term on x. So this means that the closer the point is to the left bottom corner, the better. So you can see that for uniformity, maybe SBERT with whitening is slightly better, but it's much worse in terms of alignment. So SimCSE, especially the supervised one, is getting us much better balance between alignment and uniformity. And in this sense, it gives us much more isotropic representation. If you're interested in understanding more about this, you can check this article. This is our review that we wrote with Mike Ehrlichson regarding contrastive learning. And in the meanwhile, let's see how all of this works in Python. So this is a repository that you can scan and you can follow. There are two notebooks there. I will give you a couple of seconds to scan it if you want. Okay, and now let's do it. So this is pretty easy. We can just use SimCSE library, import SimCSE object from this library, download the model. I won't do it because it takes a lot of time. And then we just encode any sentence, any phrase, even a single word, by using the encode method on the model. It takes a while usually, but not very long. And then what we can do, we can encode many sentences and just embed them in the space and perform classification on this, on top of this, or any other task. We can use it for any other task. And these embeddings will have better properties than regular BERT or Roberta. So another thing, we can also compute similarities. So here we have some sentence, attending PyData global is awesome, and another one, Jenny is hungry, sad face. And another pair of sentences is attending PyData global is awesome, and Python conferences are great. So we expect that the similarity for the second pair of sentences will be higher than for the first one. And it's true. So for the first one, the similarity is 0.14, and for the second one, 0.5.